All right, kids, here comes the last section of Unit 7. We're getting close. 7A is exponential models with differential equations. In other words, we're looking at exponential growth and decay. So if something is growing, like a population, or something is decaying, like radioactive material, you probably had science lessons and that kind of stuff. That's what this section's all about. So it's a lot of word problems, but we need exponential equations and differential equations to be able to solve them in our calculus way. So I'm sure there are ways to do it in the science method, but here's the basic equation for exponential growth and decay. You have some number in front. This is called your initial value, what you initially start out with. And then this B represents your growth or decay. Now, it's growing when B is greater than 1, and it's decaying when B is a fraction, like between 0 and 1. So if you think about it, if I were to take this thing and find the derivative of this, find dy over dt, most of these are with time. That's your variable here, time variable. Think about it, if something's growing, it's growing over time. If it's decaying over time. So that's why they use a time factor in it. A is a constant, so you stay with a constant. You're taking the derivative. And I don't know if you remember how to do something raised to a power. So it goes like this. It's times the same thing, b to the t power, times the ln of the base. If you go back to the cards that we made back in the day, you'll see what I'm talking about. All right, so if I look at that, I have it written down kind of funky. I don't think I meant what I said here. Oh, I do mean this. A times b to the t, well, isn't that what y is? Right here. I can make that substitution. All right, dy over dt equals y times the ln of b. Right, I just made that substitution. I guess I should have circled it the other way, and I can. I've got an erasable pen. All right, it's really y. So that's my substitution there. All right, looking at that, y times the ln of b. Well, ln of b is just a constant, isn't it? The ln of any number is going to be a constant of some sort. And so that means that that constant that we normally use with these things, they use it as k. The ln of b is going to be the same thing as your proportionality constant, they call it. So it's going to equal y times k. It's just a constant. And so I can say that dy over dx, you'll oftentimes see, or dy over dt, my bad, dt. I'm so used to writing dx's. You'll find that you probably will do the same thing. Equals k times y. Now I know a couple things this time in this format. Now in this format, it's growth if b is greater than 1, it's decay if b is between 0 and 1. In this case, if k is positive, k is greater than 0, it's growth. And if k is less than 0, it's decay. All right, the rate of change of a quantity is proportional to the size of the quantity. This represents an exponential model. So if you remember how we started this whole unit, we started the unit with writing directly proportional or inversely proportional or inversely, yeah, I think it was with proportional things. So anyway, this is going back to the very beginning of the unit. Set up a differential equation for each scenario. The weight of an animal is increasing. Its rate of change is increasing at a rate proportional to the weight. So it's the weight that's changing over time, dw over dt, equals, if it is proportional, it's k times, it's proportional to its weight. There you go. That was section 7.1. A bacteria population is shrinking at a rate proportional to its population size. So I guess you could say dp, the population, over dt equals, now this one's shrinking, but it's still a k factor times the population. The only thing is you can kind of make note that you know that k has to be negative. And that's because it's decaying. Now they didn't ask you that. The answer is just dp over dt equals k times p, but we know that that has to be a negative value because it's shrinking. And then the last one says solve dy over dt equals ky using separation of variables. Okay, so the y has to come to the left. That's going to be dy over y equals k times dt, or 1 over y dy equals k dt. And it doesn't matter, k is a constant. The fact that this is with respect to time, it's okay. K is just a number. So a number here and with respect to time is perfectly fine. Now I'm ready to integrate. So if I integrate this guy, I get the ln of y on the left, and on the right it's a constant, so it's going to be k times t plus c. If this were an x, it would be kx, but this one's a t, so it's kt. Trying to dig to the y, what do? Think of the loop-de-loop. E, come around. All right, so e to the kt plus c is equal to y. Now we're going to play the same game, and I'll show you one more time how this thing works. I can separate this so that it's y equals e to the kt times e to the c. Because remember, if you're adding exponents, you're multiplying like bases. And what can you tell me this is? And you say that's a constant. And so I can write it like this. Y equals c, some constant, e to the kt power, where c is your initial value. Now you're going to see in a lot of these problems that if I give you something that's set up like this, dy over dt equals k, some number, times your y, you're allowed to initially know what the function was. Remember, this is the derivative. The function was this. And so we're going to be translating when you see this scenario to go to this function a lot in this section. You'll see what I mean when we get into the problems. So that's why they put it in a box and made it special right here. They said the solution to dy over k, or dy over dt equals ky, is y equals c e to the kt. You just derived that, so you know how that works and why that is. But it represents, where c represents the initial value of the model. All right, so knowing this is going to help us. See how you have a 6 times a y? That means that your 6 is your k value, and this, when t equals 0, y equals 5, tells you your initial value. So here I go. This tells you that when t equals 0, y equals 5, that's my initial condition, my initial value. And this guy here tells me what k is. So I can go right to find the particular solution. They want to know what y equals. So y equals, my initial value is 5. That's my c, my initial value. E, k is 6, and then t. And you're done. There's no work to be had. All I'm doing is following this right here. My y equals my initial value, and I've got my k. My initial value has to be, if they gave me when t equals 2, y equals 5, I couldn't do it. That wouldn't be my initial value. Initial value has to be when t equals 0, what you're starting out with at 0. So the fact that they gave it to me at 0, I know that that value is 5. That's it. All right, let's see if we have another one here that's just as easy. All right, here's a setup. This guy's my k value, k times y. This is k. Initial value, because they gave me 0, is 4. So that means that this is my c value. And so I can do this real quick. Y equals -3. E to the 4t power, and you're done. Oh, wait a minute. Other way around. Initial value. Did you catch that? I was making sure you're paying attention, right? 4 is my initial value. That goes in front. This is a -3. That's better. Now we can use these to answer a bunch of word problems. So this is a popular one about animals and weights and things, but let's see. By the way, you need a calculator to be able to do this. So let me grab mine too while I'm talking about that. An animal weighs 3 pounds at birth and 4 pounds just 3 months later. The weight of the animal is increasing at a rate proportional to its weight. As soon as they use these words with this proportional stuff, you know you're into these differential equation things. Set up a differential equation for the scenario. How much will the animal weigh when it's 5 months old? All right, let's see if we can pick out some information here. And the first thing I know is that the initial weight, initial condition is 3 pounds, right? That tells me right here, it's 3 pounds at birth. I want to set up a differential equation where the weight of the animal is increasing, dw over dt is increasing at a rate, k, proportional to its weight. Right? So here I am, k times w. So if I want to know what w is, this is what the differential equation is, and we're going back here, k times w. Now I'm going to turn it into this guy, what the actual equation was. So I know that w then would equal my initial condition of 3, c e to the kt power. The only piece of information that I have out of all this, believe it or not, is what the initial condition is. And so your job is going to be, at this point, to find k. That's the deal. You want to know what k is. And they gave you enough information to be able to do that by this next statement right here. 4 pounds is this animal at 3 months. 4 pounds. Well, the weight is 4 pounds. I don't know what k is. I'm looking for it at 3 months. So I plug in a 3 for t, plug in a 4 for the w, and now I have one unknown, the k. I can solve for this. Let me show you how this works because it's going to involve some logarithms. I'm just going to write it a little nicer. 4 equals 3e to the 3k. Divide by 3 4/3 equals e to the 3k. How can I get the k down? Well, exponents, logarithms. I can pull it down if I take the natural log of both sides. So I'm going to make this the ln of 4/3 equals 3k ln of e. Remember, the power can come down in front as long as I take the logarithm of both sides. In this case, it's an ln because e's are involved. It's not an log. And I can move from here. The ln of e, ln's and e's undo each other. This equals 1. So all I need to do is go to my handy dandy calculator and see what the ln of 4/3 is. So let me get the ln. ln of 4/3. Sometimes it'll just pop up ln of 4/3. You know how it does that? And that's okay for now. But then I need to get k, so I'm going to divide by 3. Divided by 3. And so this is what my k value is. Now the deal with these particular problems is you don't want to round your answer until the end. So you're going to keep as many decimal places as you possibly can for this. The more decimal places, the more accurate your answer. So I'm going to say, since I ran out of room at the bottom there, k equals 0.095894. That's what the calculator told me. Did I answer their question? Because sometimes they asked you just what the k value is, what the proportionality constant is. This time they didn't. How much will the animal weigh when it's 5 months old? Well, here's what your equation looks like. Remember this guy over here? You now know what k is for this. So w equals 3e to the 0.095894 t power. Well, what's t in our case? T is 5. So I'm going to replace that with a 5 months at 5 months, what would this be? And so again, I go to my handy dandy calculator and I put into my calculator. Okay, let's see. Maybe you can't see. Now you can kind of see. E. Actually, yeah, I'll do it that way. E first. E is this guy. E to the 0.095894 times 5 power. And I get 1.61522, but then I need to times that by 3, right? That gives me 4.845. Now I'm able to round. My final answer I can round. You don't want to round till you get to the final guy. So 4.846. The weight is 4.846 pounds. That's how much that animal would weigh after 5 months. And so that's why these crazy differential equations come into play with exponential growth and decay. And that's what this section is all about. All right. We have a little bit more notes, one more problem, and this one's more like the science type thing. Talking about half-life or doubling time. You see that a lot in science classes. The growth model in our box here. Growth model has a positive exponent. Kind of makes sense. It's something that's growing, hopefully like a bank account. And decay is a negative exponent. So that kind of makes sense. They gave you examples of what they look like. Population y grows according to the equation dy over dt equals k times y, that same constant times y, where k is a constant, t is measured in years. If the population doubles every 7 years, what's the value of k? So we know, and this is the really hot topic here for this section, dy over dt, whenever you see k times y, you know the original function y, this is the derivative, you know the original function is ce to the kt power. It's just the facts. We derived it back in the beginning of this section, so you kind of can see how they go. But now I fill in what I know. Well, I don't know much, but I know that it doubles every 7 years. So what do I start with? My starting place, my initial value for this, I'm just going to start with 1. And it doubles every 7 years. That's my t. Right? And if it doubles, that means it ends up at 2, doesn't it? If I have whatever it is, starts at 1 and it doubles, it ends up 2. So what I really have is 2 equals e to the 7k. How can you solve that? And so you say, I want to know what k is. That's what they asked me for, the value of k. And in order to get to that, it's in the exponent form. The only thing I can do is to drag it down is to take logs. So ln of 2 equals 7k, ln of e, which is 1. And so k is going to equal, sometimes you'll see it this way, the ln of 2 over 7. That's an exact answer because there's no rounding that's involved in that. Or if you did actually go to your calculator and calculate it out, it comes out to be about 0.099. That's it. So you doubled whatever it is. That seems like it's a really complicated question. It's really one of the easier ones. All right, couple of practice problems, and then we will call it a unit, not only call it a day. Number 6 was the first one I picked. Kind of like the one we just did. A population y grows according to the equation dy over dt equals ky, where k is constant, t is measured in years. If the population doubles every 11 years, what is the value of k? All right, I'm going to give you a head start. You try it and I try it, and we'll see if we match. All right, it's a doubling thing. So it started out with 1, ended up with 2. It doubled in 11 years. And so you have 2 equals e to the 11k. The only way to bring that power down to get to the k is to take the log of both sides. Ln of e is 1. So you've got the ln of 2 over 11 is your exact answer. And you can see I used squiggles this time. They probably prefer the squiggles because it's an approximation. You actually rounded that 0.063. So either answer is a valid answer. Again, if it were a multiple choice question, you might see it written this way, or you might see it written that way. All right, just a couple more. Number 7 is next on my list. Number 7 says a lot. And really the answer is very simple. So let's see if we can decipher it. A certain animal weighs 30 grams at birth. During the first 4 weeks after the animal's birth, its weight in grams is given by the function w that satisfies the differential equation dw over dt equals 0.01 w, where t is measured in days. What's the expression for w of t? In other words, what's the original function? And we know the original function has to fit the format, and I'll put it up here, what it normally would be. Y equals ce to the kt power, right? That's what it would be. So do I know what c is? And you say, yeah, that's the weight at birth, right? This is my c value right here. This is telling me c. So c is 30. I don't know e, I don't know k. Or actually, do I know k? I do know k. I don't know the time. I know k because remember how it's k times y? In this case, my k is 0.01. That's my k value. So I have 0.01 up here, and then t, and that's my answer. That's it. You're done. So even in all that verbiage, they kind of gave you your pieces that you needed. You just need to fill them in. All right, number 9 is next on the list. Let me see if there's any others beyond that. There is not. Number 9 is the last one, but it's a doozy woozy. It's several parts. Okay, so be ready. We'll see if we can decipher what it's telling us. A population of fruit flies is increasing at an exponential rate. They do exponentially populate, that's for sure. I remember in college doing an experiment in biology with fruit flies and how many had red eyes and how many had black eyes or something like that. But we had to wait like several days, and they're crazy. They generate a large population pretty quick. All right, the population of fruit flies is increasing at an exponential rate. If on the 3rd day there's 400 flies, I'm just going to make note of that. On the 3rd day we have 400 flies. And the 7th day, there's 600 flies. So 7th day, 600 flies. Approximately how many flies were in the original population at day 0? In other words, what are they asking you for? They're asking you for the initial value. What was C? What did you start with? And you're like, I have no idea. Right? So let's go back to our formula. The formula that we're using, y equals, we're looking for the original formula, ce to the kt power. Well, here's what I know from this first piece of information. From the first piece of information, I know I have 400 flies on the 3rd day. T is 3. So y is 400, ce to the k times 3. Or in other words, I have 400 equals ce to the 3k. Now likewise, what do I know about the second statement? Same idea, right? 600 equals ce to the 7k, right? K times 7, 7k. And I'm trying to find C. So here's what we're going to do. We are going to solve for C in this guy. In other words, get the C alone. So I have an e to the 3k that I don't like. I'm going to divide by that. So it's this is going to be 400 over e to the 3k equals C. This guy, same idea. If I divide by e to the 7k, I'll have 600. I'm going to write it down here a little closer. 600 over e to the 7k equals C. Can you see where it's going? I'm trying to find C. So if this equals C and this equals C, then these two things must be equal to one another. So I'm going to set that up. 400 over e to the 3k equals 600 over e to the 7k. All right, so I'm looking at this, and now I'm trying to find k in the midst of all this craziness, figure out what k actually is. So I see it's a single variable. I only have one variable involved, which is awesome, because I couldn't do that back up here. I had two variables involved. So now that I only have one variable, I can calculate this out. So I know I tend to think cross multiplying, but you could also use rules for proportions. If you wanted to, you could put 400 over 600 equals e to the 3k over e to the 7k. I'm going to go cross multiplying because that's normally the way that I do it, and I showed you to do it. So let's go on a cross multiplying mission here. I have 600 e to the 3k equals 400 e to the 7k. So if I get the e's on one side and the numbers on the other side, I can divide by 400. So 600 divided by 400 equals, and I can divide this side over here. The e to the 7k is still there, so it's e to the 7k over e to the 3k. And then I can simplify that. 600 over 400 is 3 over 2 equals. And these are like bases. So if you have like bases, you're allowed to subtract the exponents. This becomes e to the 4k. All right. So I'm looking at this one more time. And I have a variable that I'm trying to pull down in front, which means I need to do logarithms. So I'm going into the next box here. The ln of 3 halves equals 4k ln of e. And again, ln of e is 1. So I go to my handy dandy calculator and I calculate out what is the ln of 3 halves divided by 4, and that's going to give me my approximate k value. So in your calculator, when you do that, you should get 0.101366 or so. Did I answer the question? Was the question asking me for the k value? How many flies were in the original population? Nope, I'm trying to find C, so I'm not there yet. I have choices though at this point. I can take my equation for the 400 equals, or I can take my equation for the 600 equals and figure out what C is. I can pick either of these, right? C equals these things, and now I know what K is. It does not matter. I'm going to get the same answer if I plug it into this guy as if I plug it into this guy. I'm going to go for the smaller values. So I have 400 over e to the 3 times 0.101366. And that, my friends, will give me how many fruit flies I came up with. It is just shy of 295. I think it's 294 point something. Oh gosh, there's Levi. Say hello, Levi. And that's how many flies you end up with. He couldn't have waited like 2 seconds for me to finish the problem. We're gonna have to train him better. All right, there you go. Fruit flies. All right, that takes care of section 7-8. It also takes care of the whole unit. So work on your mastery check. That is due for Monday, along with all these lovely sections. There's no problems to eliminate in this one. There's really not that many to do. All right, shoot me an email if you got questions. I'm really proud of you. Keep going. We're almost there. And I'll see you in class.